This is my Lab 5 retros exam collisions. The goal of this lab was to compare the true motion of two cards after a collision with predicted motion. The system included two cards, the track that they were on, and their surroundings. It's just the air. The key physics principles in this lab are in second law, conservation of momentum, and kinetic energy. And I found that in reality, not all energy is transferred during collisions. Some is lost in surroundings, resulting in a difference between true motion and expected motion. So Newton's second law says that force is equal to mass times acceleration, and we use this in position and velocity update equations to examine the motion of particles. Conservation of momentum says that the total momentum before a collision is equal to the total momentum after a collision when the collision is elastic. And kinetic energy is calculated by 1/2 times the mass times the square of velocity. To analyze this, I took two cards and had them collide on the track, and I plotted their motion in tracker. I set the initial conditions. I set the mass of both cards to 1 kilogram, the initial velocity to be 0.604 meters per second, which I calculated by taking the first two positions from tracker and the time interval. And I used this loop to update the position of the cards as they move to the right, and then once the second card hits the wall, it moves back to the left. I calculate the kinetic energy for each card here. This is the graph that the glow script generated, where the left card moves right, it's the blue card, the right card stops, gets hit by the right card, and then moves back to the left. Kinetic energy goes from maximum to 0, back to maximum, because all of the energy is transferred. Time versus X position for the blue card shows that it is at rest, then it begins moving to the right, back to the left after hitting the wall, and then at rest again. Kinetic energy goes from minimum to maximum, back down to 0. This is the comparison of the experimental and computational graphs. They look similar, but there are some key differences. In the experimental model, we see that the left card doesn't actually stop and it continues moving to the right, maintaining some of its momentum, whereas in the computational model, we predict that all the momentum and energy is transferred, causing it to stop. And then also, in the second card, we can see that it begins moving back to the right a little bit after its second collision, which we don't see in the computational model. So if this was some error that could be present in this lab, we're not clicking the same point in tracker each time, not accounting for external forces in the computational model, such as air resistance. In the computational model, we assume that no energy is lost in the surroundings, and we also assume that all energy is transferred to the other card in the computational model. So is the energy principle satisfied from the model system? In the model system, all momentum is transferred between the cards. This means that all of the kinetic energy is transferred during the collision and none is lost in surroundings, which proves that the energy principle is satisfied. And how would the graphs differ if the collision is perfectly inelastic if the cards stuck together after colliding? The x-position graph of the red card would continue to increase before the two cards hit the wall. However, after the collision, its velocity would decrease. Kinetic energy graphs would be very different. In a perfectly inelastic collision, energy is lost in surroundings in forms such as heat. Though the momentum is conserved during this collision, the energy drops greatly. We can also infer this from the calculation of kinetic energy, as even though the mass of the system doubles, the velocity falls at a greater magnitude. And that concludes my lab.